Okay, imagine we have a situation with 2 points in space, P and Q. And without any loss of generality, we'll just leave Q where it is and we can move P around. We'll say there is an infinite distribution of matter in the universe and we want to calculate what is the contribution to the gravitational field at point P from all of the infinite matter in the universe. What do you think? Should P be attracted towards Q, away from Q, or should it not be pulled in any direction at all? Think about it. There's an equal amount of mass everywhere in the universe. It goes on forever in every direction. There's nothing special about uh, the masses at P and Q. They're neither heavier nor lighter than the other masses in the universe. Yet some people think that point Q is relevant to the question about the gravitational field at P, even though there is absolutely nothing to pick Q out as special. They say P is attracted towards Q, and it has been proven beyond any shadow of a doubt. Well, a little later on in this video, I'm going to try to hypnotize you and see if I can convince you that their argument is right. Before that, though, I'm going to try to convince you that it's wrong. I'm going to say there is no force on P at all in an infinite homogeneous universe, or no net force anyway. Let's start with a little finite group of masses represented by a few dots. As I move P into the region where the masses are, this little purple line appears. These little purple lines appear. Showing the contribution to the gravitational field at point P. Point P is moving here. The masses are not. So when P gets close to a mass, there's this really big purple line. The direction of that purple line points away from P because the mass is pulling toward itself. The length of the purple line gets really long because it's proportional to the inverse square of the distance. When you divide the square of a little bitty number, you get a really big number. 1 over 0.1 squared is 100. 1 over 0.01 squared is 10,000. 1 over 0.001 squared is a million. Now I arranged these dots so they wouldn't get too close to P, or these lines would just get crazy big. But it gets a limit. That's the closest it can get to the dot. And next, what I'm going to do is provide a little bit of shading. Okay, now what I've done is to show this darkest area where there's a significant contribution to the gravitational field at P. And outside that region, there's less significant contribution to the gravitational point at P. So as I move this around, you'll see that all of the larger arrows, as you can see, the masses outside the darkest circle here contribute virtually nothing to the gravitational field at P. I can zoom in on the dots and show you they do contribute a little bit, but it gets more and more negligible as you get further away from P. Now, if we have an infinite homogeneous distribution overall, the contributions of all these different masses should cancel out. We can pull back and look at the overall shape of that shaded region and see that it is completely symmetrical around P. So there should be no net gravitational field pulling a mass away from P. Now let's turn off those little masses there, and what we're doing is we're assuming that a homogeneous distribution exists everywhere in the universe. If you have that infinite homogeneous distribution, you can see that Q has absolutely no effect on which masses affect P. I move P around, and the contributions to P move around with P. They don't at all move around with Q. So, are you convinced? I'm pretty well convinced. I don't see any possible reason that making some arbitrary choice of point Q could have any effect on the gravitational field at P. On the other hand, don't you want to believe that there is a force on Q from P? Maybe I could give you a convincing argument that there is a force towards Q. or failing a well-reasoned argument, maybe you could just be hypnotized into believing it. All right, well, you're going to take a deep breath. Let it in, let it out. Let the tension out of your body, relax. These are ideas that are beyond human comprehension. Open your mind to the impossible and focus on point Q. You are entering a deep, relaxed, hypnotic state. There is nothing in the universe except Q. Focus on the expanding rings around point Q. And relax, enter a deep hypnotic state. There's nothing in the universe except Q and the expanding rings around Q. See the symmetry of Q? Is there a symmetry around P? You no longer see it. You no longer see it there. You have forgotten the symmetry around P. Here, it is gone. There is only a symmetry around Q. When I snap my fingers, you will awaken, and no matter what question I ask, you will insist that you will insist Q has relevance. If I ask you the name of your dog, that dog is symmetry around Q. If I ask you to cluck like a chicken, the cluck is symmetry around Q. If I ask you the gravitational potential at P, the answer is symmetry around Q. Now, hopefully, okay, so hopefully my cell phone interrupted things, and I'm not a good hypnotist, so you might not be convinced that you have to invoke symmetry around Q when clucking like a chicken. But have I convinced you that you have to invoke symmetry around Q when calculating the gravitational field at point P? In other words, did I convince you that I was wrong earlier? The next sentence I will say will be gibberish to you, but in my earlier argument I said to count the highest contributions to the gravitational field first. You cannot currently see the shading here, or see what I am doing with my mouse. You can't see this circle here where the shading is darker. It's impossible for you to see because you are hypnotized. Now, you will understand clearly when I tell you you don't count the highest contributions to the gravitational field first, but instead invoke the symmetry around Q. Will you do it? Are you hypnotized enough by this growing pattern around point Q that you're going to focus on Q and Q alone? All right, sure, why not? Let's be hypnotized. Let's see what that looks like. The red or orange circle that is expanding. Let me move Q over here so we can get a little bit more on this. Okay, so the red circle you've been hypnotized by here is counting up all these little volume elements around Q. When you add up all the contributions from all these volume elements, you get a contribution to the gravitational field at P towards Q. On the other hand, when that shell grows out to a radius beyond P, the contribution of that external shell contributes no gravitational field at all towards P. The net effect then, so long as you keep hypnotized by Q, is that you are going to believe with all your strength that there is a gravitational field on P towards Q. And there won't be any argument that can convince you otherwise, unless you manage somehow to break hypnosis. But you know what? I'm not going to break your hypnosis right now. I'm going to make you go deeper into hypnosis. I'm going to show you how Newton's shell theorem is derived. You won't be able to break free of the hypnosis after this. Is there any other geometry in the universe except for its symmetry around Q? No, of course not. There is only Q. Okay, to derive Newton's shell theorem, we're first going to imagine breaking up this shell into little rings. I don't show the rings well in this diagram because the rings are perpendicular to the screen. What you want to do is think about the circle as a sphere, and then this line, this vertical line here, this line here is actually the ring, and the numbers 0, 90, 0, 90, 180, and 270 represent angles around the ring. You can imagine the ring kind of going into the screen, then being on the opposite side at 90 degrees, 180 degrees down here, and then back out of the screen up here. So that is our ring. Once we have established that ring, once we have that ring established, we're going to slide the G points to other locations on the shell. And we're going to add contributions from every part of this shell. Doesn't matter whether we take the contributions left to right or right to left. No, not at all. Why would you think that? As long as we account for all the masses in the rings, it couldn't possibly matter what order we take them in. All right, but then we go on to the next shell. We're going to lift this up to the next shell. And here we can go either way, increasing our radius outward or decreasing our radius inward. It doesn't matter what order we take our shells, so long as we count for all of them. Doesn't matter what order we take our shells? Not one bit. Why in the world would you think it mattered what order we took the shells? Don't be ridiculous. Now look at this. When we move the radius, move the radius so that P is outside the circle, we get a force, or we get a gravitational field towards P. But when we move the radius so that it is inside the circle, we get a gravitational force. We don't get a gravitational field at all. So there's no need to add these shells in a particular order either, right? Of course not. All right, just in case you're a mathematician, or even if you're not and you'd like to be, I will even show you the proof. First off, let me say this is a 15-line proof, so it's pretty big. I'm going to show you the whole thing before we get started, and then this will let you know just how long a ride we're in for. Steps A through D here integrate over the polar angle. Steps D through K, which probably contain the most unique mathematical steps, do the integral over the azimuthal angle, and finally steps K through O take care of the integration over the radial direction, which lead to these piecewise defined descriptions down here. Okay, so I'm going to go through each step now. Step A here. See the A above the equal sign? I like to put letters above my equal sign because that's where things are done, in the equal signs. Step A is the gravitational field is equal to the volume integral of the density over distance squared times the gravitational constant g times a unit vector L, unit vector I've called L. Now I want to point to what that L value is in the picture. L is this distance here from the point that we're considering, the point where the gravitational field is actually being calculated, you're hypnotized not to realize that that gravitational field will be zero, but we're going to, so we're looking at this point here and saying, okay, this point over here on the ring is pulling in that direction, in direction L, from P towards G. Okay. So we want a unit vector in that direction from P towards G to tell us what direction this gravitational field contribution from this little bitty element right here is. So that brings us to step B. We're breaking down the differential volume element into little cube-like structure. The thickness and width are shown in the demo, but the arc length is perpendicular to the circle, so you just have to visualize that. So all these little bricks in here, the height of the brick is dr, or delta r, and the width of the brick is r d theta 1. Of course, the widths of the bricks that I've drawn aren't actually r d theta 1. I've arranged so that each brick has the same width, so the calculation wouldn't. So these are actually different widths. The width is actually proportional to the radius in this kind of differential volume element, but that's okay. There's an accounting of that done in some of the other math. So step B, we broke things down into the differential volume element, and step C, here I break the unit vector unit vector L sub x, L sub y, L sub z into sine theta 2, cosine phi, sine theta 2, sine phi, and cosine theta 2. Where do these come from? Well, looking here, I've got these three lines, little r, big R, and L. And theta 2 is this angle out here, the external angle, the direction towards the ring from P. Theta 1 is this angle in here. And if I move this, you can see those angles both change when I move that vector around the sphere. So but anyway, long story short, theta 1's over here, theta 2's over here. So I've got this function with the sine theta 1, sine theta 2, or sine theta 1 and all the functions of theta 2 over here. And what we're going to do is we're going to integrate that from phi equals 0 to 2 pi. What happens to cosine phi and sine phi as you go from 0 to 2 pi? They actually just cancel out each other. We're going all the way around the circle, and the L sub x and L sub y variables cancel out, leaving us with a 2 pi cosine theta 2. But that is in the z direction. So that is actually going to point directly towards Q. Hey, it's like we've been hypnotized to believe. It's going to point directly towards Q. Okay, so we're already getting that part of it. In step E, I get rid of the vector gravity and just focus on the z component of it, since both of the other components were 0. Now we're going to do a couple of really neat mathematical tricks that are the juicy part of the proof. First, we're replacing that sine, where is it, sine theta, there's a sine theta 1 right there, and there's a d theta 1 right there. We're going to replace that sine theta 1, d theta 1 with d cosine theta 1, because the derivative of cosine theta 1 is sine theta 1, d theta 1. So then we're going to skip forward, I'm going to skip forward to step G, because this is the law of cosines. We're using the law of cosines for theta 2 here, and we get this value. Use the law of cosines for theta 1 there and get this value here. All of the parts of that law of cosines are basically this L and this R and this R. Basically, we've expressed both the theta 1 and cosine theta 1 and cosine theta 2 in terms of little r, big R, and big L. But coming back to step F, a key to this derivation is that this derivative of cosine theta is not a function of little r or big R, it is only a function of L. So we can replace the total derivative with a partial derivative, and that makes it simplify like a lot. So watch, I'll bring it around and show you. Does little r change? Little r down here? No, little r does not change. Does the magnitude of big R change? No, the magnitude of big R does not change. So when we take the derivative of cosine theta 1 and cosine theta 2 and we express them as a function of little r, big L, and big R, the derivatives can be, or the derivative can be expressed entirely in terms of the derivative of it with respect to L. So in step H, we have taken the derivative of this, and it goes, and all that derivative becomes L over big R, little r. Now to the next page, where in step I, we have simplified our previous expression algebraically. Okay, step J, I guess we simplified even more algebraically to make it a real easy integral in terms of L. So this integral of 1 is L. Integral of a constant r squared minus r, big R squared over L squared. Derivative of 1 over L squared is negative 1 over L, I think. So yeah, so the r squared minus r squared minus big R squared became big R squared minus r squared. So that's where the negative sign went. So now in step K, we perform the integral over L. Let's, I want to show you why there's a conditional down here. Let's move the, wait. First, let's move this ring over to the right side of the shell. Hopefully I can get it over there. And you can see that big L, or little, or L is equal to, okay, the purple line. The purple line is equal to the green line plus the orange line. And when I bring P inside, you can see still the purple line, L, is still equal to the green line plus the orange line. It's good. So over on the right hand side, we've got big R plus little r right there. And then we're going to go look at the left hand side. So I'm going to drag this around over here, and you see that when I'm over here, we've got two conditions. The first one is that capital R is bigger than little r. And in that case, the distance L, the purple line, is equal to big R minus little r. And then I move this over here, and now we have that the purple line is equal to the green line minus the orange line. So that's why I've got a conditional right here that we use big R minus little r if big R is bigger, and little r minus big R if little r is bigger. Then once we plug those values in and take and do some algebraic simplification, it turns out that when little r is bigger than r, we get this value 4r, and when little r is less than big R, we get 0. And then that simplifies down, so we end up just getting all our constants outside here, and we get integral of r squared dr, simple integral. You get r cubed over 3, which ends up being an 8 pi g rho r over 3 at the end. And this is what we have if we have a finite shell of radius r sub s. Then outside that shell, we should have a gravitational field of 8 pi g rho r sub s cubed over 3 r squared. Inside that shell, we should have a gravitational field of 8 pi g rho r over 3. Okay, so great, right? But we don't have a finite shell. We've got an infinite shell. So there's never a case where r is less than infinity. So we'll always be using this first part, right? Right. That's the hypnotism. We're going to be using that because we've been hypnotized to use because all there is Q, and there's no other symmetry, right? If I ask you about your dog is named symmetry around Q. How do we escape this inescapable logic? Is there any way to escape Newton's shells? Never mind that the gravitational field at point P is completely independent of Q. How can we possibly escape this shell? I can only move R, and I can only move this thing back and forth along this shell. There's no escape, is there? No escape at all. We must stay in this shell. The symmetry is inescapable. Except it's not. Look what I can do. I can move this anywhere. I can put a shell over here, add up all of the strong contributions to the gravitational field around P, then all the second strongest contributions to the gravitational field around P, or all the third contributions. I could just go through like from negative infinity to infinity along that line, and then negative infinity to infinity along that line, and then negative infinity to infinity along that line, and then keep going, negative infinity to infinity, back and forth, back and forth. But for some reason, they want to stay here. They want to stay here in this shell. It's inescapable. They want to stay on those inescapable Newton shells so that they can convince you that there's a gravitational field towards Q on P, this completely arbitrary point. Another thing we could do is just start building Newton shells around point P. There's no reason not to put Newton shells around point P. It's just they decided to put them over here around Q for some reason. If you're just going to add up the contributions to the gravitational field around point P towards point P or away from point P. So does anybody remember the reason that we chose point Q as a point of symmetry? Anyone? Truth is, I gave you absolutely no rationale for choosing Q as our point of symmetry. I just gave you a hypnotic suggestion that you should. However, I did give you a pretty solid reason, I think, to create your symmetry point around point P. The gravitational field strengths of those masses in the general vicinity of P are much stronger than the contributions from elsewhere. So in order to not get the wrong answer, you should add together all those big contributions and then not really worry so much about the little bitty contributions that are far away and not really all that much concern to the gravitational field at point P. So even if someone picks a point of symmetry over here at Q, you should still add things up according to the magnitude of their contributions. Use these little guys first. Come down here where the darkest regions and the strongest poles, use those areas, and then come out to these weaker areas if necessary, and then you can pretty much just ignore what is outside that, because those are not much pools. They're symmetrical around P. You don't have to worry about them. Now this idea has the benefit of making sense. Everyone should agree that the gravitational field at P is independent of the arbitrary point Q, and they will all agree what the field actually is. They will all agree it is zero. Unfortunately, it does not have the same mystique as the nonsensical hypnotized claim, the mystique of working through Newton's shell theorem, the mystique of applying it to an infinite homogeneous distribution, the mystique of getting a different answer depending on where you put Q is, but saying it's always the same answer. All kinds of mysterious things you can do by hypnotizing yourself into thinking that you have to stay in Newton's shells. Good luck.